Hello, everyone. So thank you so much for coming for this talk. As mentioned, this is display monitor research of the ongoing research that I'm doing. So definitely, like, if you have views, if you have insights, do come up later. I'm happy to talk to you about display monitors and how we can improve this research. So quick introduction. I do AppSec in government, the Singapore government, and hacking is my hobby. I have hacker handle Space Raccoon, so you can just find me online. I'm on Twitter, GitHub, the usual. Okay, so for today's talk, what will I be going through? I'll first be going through the foundational protocols of the display monitor research, DDC-CI and MCCS. And then I'll go into manufacturer-specific VCP codes, so opcodes that are sent over this protocol and why they're interesting. Then I'll talk about some possibilities of host-to-monitor exploitation before going to monitor-to-host exploitation, which is also interesting, and then further research. So I'll start with some background on what these two protocols are. And before that, gotta acknowledge some prior work. So actually the guys are just right next door. The Red Balloon security guys, they did it in 2017. Ang Cui is there as well. So if you see him, you can also chat with him about the work they did. They worked on the GPro protocol, which is a separate protocol from MCCS. It's a debugging protocol that also kind of runs over the same physical link on channel as well, DDC2 BI. Max Thomas has also done some research on reverse engineering display monitor firmware. Not the most exciting, but also very challenging because of the instruction sets that they use, and very different from what you typically see in other firmware. So yeah, let me know if there's more work as well. Definitely happy to chat about this part of research. So there are two key protocols behind display monitors. The first is Display Data Channel Command Interface, DDC-CI. This is basically the bidirectional protocol that allows devices, hosts, to chat with talk with the display monitors, and this runs over the physical link layer. And it's actually separate from MCCS, which is the Monitor Control Command Set, which is again a more high-level protocol that describes a set of controls that software running on the host can communicate with the display. And the interesting thing about this is that there is a version 2.2a, which was released in 2011, even though there is a version 3, but none of the manufacturers actually implement version 3, so it's kind of just version 2.2 most of the time that you'll see. And both are maintained by the Video Electronics Standard Association, VESA. So you probably know about the VESA mount, but they actually do a lot more in this space, apparently. Okay, so just break down MCCS. So what does MCCS do? The main way that it communicates with display monitor is with virtual command panel codes. And basically there's an opcode, 0 to 255, representing various commands, for example, like brightness, contrast. And then these opcodes have different types. So they can be write-only, read-only, or read-write. So for example, you may want to read and write a brightness setting, but you may not necessarily need to write, for example, metadata that's stored on the monitor, like the serial number. And then there's also different data types. So the first, again, this is all a single byte stuff. So the continuous is from 0 to 255. Your brightness can go from 0 to 100, for example. There is the non-continuous. So this is an enum. So, for example, you may have a display setting, a display mode for game mode, movie mode, theater mode. These are enums, right? 0 to 5, 6, smaller ranges. And then a bit more interesting is that some of these codes support table data block types. So these are ASCII strings or other types of data. These tend to also have very specific implementations and very specific to the type of the code. So there is well-documented standard VCP codes. This is a specification. It's supposed to be private, but you just Google it and it's right there. Basically, it's just a list of the standard commands that you would send to a display monitor: gamma, contrast, luminance, brightness, and you can also look at different types and the functions that these codes support. The more interesting part that I wanted to look at was the E0 to FF control codes. So these are the last 32 bytes opcodes that are reserved for manufacturer-specific controls. And the VESA MCCS specification warns that you probably shouldn't use this as much as you think you should, because manufacturers can specify their own opcodes. This can lead to a lot of incompatibility. But good luck with that, because manufacturers love adding their own features these days. So now you have monitors that support webcams, monitors that support all kinds of strange features, and this is also operated over MCCS through these last 32 bytes. And they all differ from manufacturer to manufacturer. And another interesting data type or message that is part of MCCS is the capability string. So this is basically, the initial handshake or just fetching metadata about the monitor you've connected to. This is what it looks like. This is the capability string. And it tells you, for example, what VCP codes are supported by that monitor. And you will see, for example, for the non-continuous VCP codes, they also have additional parentheses that specifies the possible range of non-continuous values. And one thing I found while doing this research is that this is actually often very inaccurate and cannot be trusted. So manufacturers are pretty lazy. They'll just, give you a standard value. So most of them are actually just from the same OEM or a white label, and often includes metadata about the display monitor that's also inaccurate. So it's just there because you need to do an initial handshake, for example. Yeah, so just remember this is a surprise tool that will help us later. On Windows itself, there is a kind of standard set of Win32 APIs that interact with MCCS. In particular, you would look at capabilities request and capabilities reply. This fetches the capability string. There is get VCP feature and VCP feature reply. Again, this is for read of a VCP code. And then the set VCP feature. So these are pretty low level. The higher level stuff are just wrappers around them, but they are pretty useful. So these low-level APIs are typically called from .NET framework binaries. These are you can see the display monitor software I had on the screen, the Acer display widget, but every manufacturer has their own display monitor. If you're a gamer, there are some gaming specific software that you can also use. And these kind of abstracts away a lot of the VCP function types by wrapping around the low-level Win32 APIs. This is a common pattern, but it makes it really easy for us to reverse engineer. So one thing about this API is that according to the specification, the VCP code should also return the code type and the maximum value when you read VCP code. But again, manufacturers often ignore this. So you would expect, for example, in this case, when you read from a specific VCP code, you would get the code type as well as the maximum value of that VCP code. But often this is just 0 or completely just wrong altogether. So I've looked into this as well. So quick summary, again, for introduction to DDC CI and MCCS is that it's a fairly narrow attack surface. It's really just 0 to 255 opcodes, limited range of possible values that you may think so. And there's often non-conformant. So there's a lot of variance in how manufacturers implement this specification. And it's also accessible with the lower level user mode Windows APIs. Okay, so let's talk about manufacturer-specific VCP code. So what are manufacturers doing with this protocol to add functionality to their display monitors? So it's fairly easy, as I mentioned, because a lot of the client-side software is easily reversible .NET framework binaries. Some of them are C++, but again, not too hard. You can retrieve a lot of these manufacturer-specific VCP codes from the software. So, for example, for Dell, you do have some interesting controls such as monitor privacy controls, which flips on and off stuff like your microphone, your built-in microphone, your zoom. There is also a multi-monitor sync. So this is kind of like when your monitors are kind of synced across your two devices and you can kind of drag and drop between them. And it's also easy for you to figure out the expected range and enum values. And this is also very helpful when you're trying to figure out what manufacturers have implemented. The problem is that there is a lot of software, right? There is display widgets. They have different versions. Some of them are from the same white label manufacturer. So I've noticed stuff like AOpen is using the same backing DLLs as Acer display widget, again, from the same Taiwanese manufacturer. So you do see a lot of overlaps and similarly the same vulnerabilities. Other than static analysis, you can also fuzz VCP codes. So what I do is pick just, it's a fixed range. It's not too hard to just fuzz the limited range of values. But it's kind of black box fuzzing. So your monitor will kind of blow up or turn off and you kind of don't know why it did that other than the opcode that did that. So it's not great. What I've typically used fuzzing for in this case was just to test for deviations from the standard MCCS specification. So, for example, there will be certain VCP codes that are read-only for a good reason, but are surprisingly writable, and that's an issue, and vice versa. But in general, black box fuzzing doesn't really get you that far. One interesting way I've done this research as well is a dynamic analysis with hooking. So Frida, you can just hook the low-level Windows Win32 APIs and just use the application as you would normally. And this is a way to just kind of figure out, for example, for the manufacturer-specific codes, what the enums correspond to, especially if you don't have an easily reversible binary. So this has helped me kind of enumerate all of these manufacturer-specific codes, their enums, as well as their expected behavior. So one thing that was pretty cool while I was doing all this reversing work, just trying to understand this protocol a bit more, is that some manufacturers have very strange ways to get around the limited set of opcodes that are reserved for manufacturers. Remember that there are only 32 bytes that are given for manufacturer opcodes, but what some manufacturers, for example, with Acer, is that they do sequential writes. So let's just quickly dive into this pseudocode. What you see is that they first set the VCP code for EB to 7 or 5, and then afterwards they perform the actual write with the second set VCP feature using the EC opcode and then the actual value of the sub opcode. So what you see is that the first set VCP features is to tell the monitor, okay, my next write, I'm going to write for this hidden opcode, and then my next write is going to write to that value for that sub opcode. So what this means is that theoretically, for one manufacturer opcode, you can then have 32 sub opcodes, and this helps them to really expand the type of functionality that they need, especially since nowadays with all the features you build into displays such as gaming and webcams, this helps to expand that a little bit more. Other ways that I've seen that displays software has done this, for HP, for example, they do something called sub-byte packing. So they would send a continuous value, but this will be a series of hex bytes, and the first hex byte would actually be the subcode byte. So they are not actually setting a specific VCP code, they're actually setting for that sub VCP code using the sub byte. Again, this helps them to pack more information into a single opcode and also more features as well. So that's it for the manufacturer-specific code. There's a lot of variance in the purpose and implementation of these codes. They're both static and dynamic analysis method that you can use to reverse engineer them. And it's far more than 32 possible VCP codes in reality. So it gives you a lot more interesting work to do. So let's talk about host-to-monitor exploitation, where we find some interesting VCP codes that manufacturers have implemented that can be dangerous. So as a quick review, for example, Dell allows you to kind of turn on and off the monitor switch for the microphone. Asus has kind of on-screen display stuff. You can put a little dot or some stuff like that, manipulate the display on the computer and make the monitor kind of show stuff that you typically wouldn't expect. HP allows you to kind of turn on and off again the file transfer, device bridge, which is kind of when you kind of copy and paste between monitors. And you probably don't want any random program to trigger this, but MCCS as a specification doesn't have built-in authentication or authorization. And what was interesting is kind of hard to kind of argue that it's an exploitable bug. It's a feature, not a bug. And MCCS by default does not bake in authentication. But there are some interesting cases. So what I found previously in HP displays is that they had an anti-theft feature. And what this does is that you can actually set a pin using the HP display monitor software so that if your monitor is taken away and plugged into a different computer and you don't enter the pin, it just gets locked and you can't use it. I mean, it's not a great anti-theft feature, but they have it anyway. And how it works is that it uses 3 sets of manufacturer-specific opcodes. The first is FC theft low pin. This set is a 6-digit lock pin. So the first this low pin just sets the lower bytes of that 6-digit pin. And then the next is theft high pin, which is FD, which again sets the higher bytes of that pin. And finally, you enable or disable the theft deterrence feature using F8. Of course, this is kind of dependent on whether deterrence has been enabled or not. So if it has been enabled and you send the wrong pin in the first 2 sequences, then you won't be able to change the theft deterrence opcode value. But if you do, then you are able to do that. And it's one interesting thing was that they actually made a mistake here, which is that the TEF low pin and TEF high pin opcodes, you would typically expect them to be write only because that's where you write the pin and it checks whether your pin is correct. And in this case, they had made it read-write. So even though someone had set the anti-theft pin, you would still be able to read that from any other software and just fetch the pin and unlock the monitor and bypass the anti-theft feature. So this is kind of an interesting case where you bypass the command logic of a VCP code and are able to exploit it. But that's really at the high level. So let's kind of look at some interesting memory-specific implementations that deal with the monitor's memory. So in this case, we have a feature by Acer where they're able to fetch the serial number that's stored in the monitor itself, display monitor itself. And what it does is that it does kind of a sequential read of data. So it would say it would use the E0 opcode in order to start the read, and then it would use E1 and an offset. So it would actually run a set VCP feature that would tell the monitor that, hey, I want to read at this offset in memory. And then later you run a get VCP feature where you fetch from where it would basically copy that memory into this block, and you'll be able to fetch it using E1. And in this case, they had artificially limited this in the offset. As you can see, they set offset equals 5, but actually you can set the offset to be more than 5. I haven't been able to get a lot of interesting data from that, but give me more Acer monitors and maybe you can read more interesting things in memory. So this is something that you can look at. This is something I've written a quick script for, wrapper around the low-level monitor APIs that will allow you to then read or write strings, theoretically, with more monitors, but I do need more Acer monitors to test this against. So quick summary is that for the host-to-monitor exploitation scenario, there is still fairly limited, I would say, exploitability potential for now. Mostly getting around it's a feature, not a bug, right? Like, hey, you can turn on the webcam or you can turn on the microphone. Maybe that's not ideal. Maybe you don't expect your Zoom to be able to turn on your microphone without you knowing, but it can be argued that it's also a feature. And it's also very challenging to test and reproduce. So how do you emulate monitor firmware? And also trying to get advanced display monitors is expensive. So what I ended up doing was I go to the Singapore equivalent of Best Buy and tell them I want to check out the monitors, and I plug in my laptop and run some scripts and hope they ignore me for a while. But it's gotten pretty iffy sometimes. So one thing I really want to explore more is more of these out-of-bounds memory read stuff. The challenge is then how do you exploit it, right? Because if you can write memory on the display monitor, and you know there are several debug protocols like gprobe, for example, and Max Thomas has also found some stuff with the LG monitors. Sure, you can write, but it's not like you're going to be running a reverse shell on a display monitor in OpenRISC. I love to see that, but not super exploitable. And you can read, so you can read other parts of the display data, may be valuable depending on your implementation of your monitor, but once again, very dependent on the model, the instruction set, and also you just need to test this against a real monitor, and it's kind of hard to kind of do that without an emulator. So ultimately, I moved on to monitor-to-host exploitation, which I thought was pretty interesting. And just to recap, there's a lot of monitor software out there, right? And all of them have different applications. Some of them just flash the firmware. Some of them help you just change the brightness. Some of them are more gaming specific. And some of them are pretty interesting. They allow you for remote administration of monitors across a network. So for example, if you're in a big enterprise network and your device's endpoints have this installed, this will allow you to configure the monitors they're connected to remotely. So again, pretty interesting exploitation potential and a wide attack surface in general. As mentioned, it's also a lot easier to reverse engineer and run software instead of monitor firmware. So there's a fixed set of APIs that are in Windows, Win32, that allow you to use them as sources for taint analysis. So you just start from there, you work forward, and you see where all of this is used. In this case, what you see here is the HP Display Center binary. So I had an idea, which was that MCCS responses are generally trusted. So what happens if they are used unsafely and controlled by a Trojanized display monitor? So if you recall, for example, the get VCP feature and get VCP feature reply has some output buffers The first is the code type, not very usable, but then you have current value and then maximum value. Again, not great because they tend to be just single byte stuff, but you do see some cases where manufacturers do implement a string reader, right? So in this case for Acer, they kind of read it in blocks of like I think six bytes, and then they convert it back to ASCII, and this is then used in the rest of the software. So what does it do with the decoded string? In the case of Acer, after reading the serial number from the display monitor that's stored on the display monitor, it would actually create a registry entry and append that to the Acer display widget directory. In this case, it was interesting. You could kind of traverse it a little bit, but there was somewhat limited set of characters you could use, and you couldn't get too far with that. But it was still an interesting case where if you had plugged this into the wrong monitor, you'd be writing random registry entries in your computer, which is, again, not ideal. But if you recall from earlier, I mentioned that there is the capability string, which is the MCCS capability string, that's controlled by the display monitor. And this is actually far more used by a lot of other software. It also gives you a lot more characters to work with. The ASCII is not super strict. It kind of just reads everything. And also it allows you to have, again, a lot more opportunities and software to work with because it's not manufacturer specific. All display monitor software has to support the MCCS capability string. So we'll do a quick exercise. Let's spot the mistake in monitor decode VCP string, which is in these DLL used by several monitor software. So it's kind of a white label, I think, Taiwanese manufacturer that uses this. And so let's not spend too much time trying to parse this. So as mentioned, your VCP capability string has a VCP in it, and then you'll have a list of the opcodes that the monitor supports. And in this case, it's looking whether the monitor supports the E0 manufacturer-specific opcode. And in particular, this is a non-continuous value, which means that it will have a start parenthesis and then a list of the possible values that are supported by this non-continuous opcode. But in this case, it will keep looking for a close parenthesis, and if you don't provide the close parenthesis, then it's just going to keep going and make the memory copy in your heap. So the theory was that by sending an Evo MCCS capability string from a Trojanized monitor, anyone running this software can trigger an out-of-bounds heap read when they plug it into this monitor. And in this case, this is what the payload would typically look like. You just have an open parenthesis, and it will keep incrementing the mem move until it hits a closing parenthesis and creates corruption here. But the challenge is, how do I build a proof of concept if I don't know how to modify or emulate monitor software? So Max Thomas has done some good work in there. He's kind of found, similar to the Red Balloon security team, a kind of a debugging protocol to write to the active memory. But in this case, I didn't have an LG display monitor to reproduce this, and I also don't have other memory write gadgets for other manufacturers. And, it's kind of expensive to do that. So the answer is always Frida, right? So in this case, what I've done is that I've hooked the low-level monitor APIs and modified the return data inline so that we can simulate the Evo monitor and without even touching the hardware, but also respecting the data offsets and lengths so that, I can claim that it's actually working as intended. So I said demo time in here, but I think I need like a mouse or something because it needs to be like the only connected monitor and not just the laptop screen. But I did record a video, so we can use that. So what we see here is that we're going to run the Frida script to start the Acer display widget software. And it will also hook all of the responses from the low-level Windows APIs in order to return the payload responses, simulating a Trojanized computer display. So let's start here. And one thing you'll notice here is that I specifically replaced the device ID to start with ACR because the Acer display monitor searches for that in order to think that it's compatible with this software. All right. And I'm just going to hook it to WinDBG just to make sure that we get a view of the heap memory when it's corrupted. And I'm going to click, and I'm going to like just use the software as normal. Right, in this case, you'll see that I've replaced the response capability string with the E0 with just A's. But in this case, it matches the length of the original response string from the monitor. So it's supposed to be the same length. I didn't change the length at all or any offsets. This is what it should have looked like. And this does give you the heap corruption and just confirming it's exploitable. Cool. Yeah. So in this case, what happened was that by connecting to a Trojanized display monitor that sends over an eval response string or blob over MCCS, such as the capability string, your display monitor connecting to it, running in the background, will get honed over HDMI or DTCCI. So it can be USB-C, it could be any other connectivity that runs over the DTCI protocol. This is an interesting attack surface to me. There's a lot of potential targets. So as mentioned, there's this OEM that it shares this library with a lot of different monitor software, so all of them are affected by it. And it's a somewhat limited set of sources. So the MCCS capability string, table type VCP codes, as well as manufacturer-specific string or blob readers that you can kind of work with. And there's also more impact by being able to reach code execution on host by plugging it into your monitor, and gives you a lot more flexibility in terms of what you can do afterwards. So I talk about further research and my conclusion. In terms of current research, there's a lot more paths to take. What I'm looking at is testing more manufacturer-specific VCP codes. The problem is that I'm limited by budget, so I need to buy a monitor each time I want to test a new interesting manufacturer-specific VCP code. Some of them are far more advanced. For example, the webcam stuff, those cost thousands of dollars. And there's also software that does display monitor administration over the network, which also has interesting possibilities. There are also more memory read and write gadgets that I would like to explore, not just the ones that we have found so far, but by being able to do that, you maybe get more insights into the actual running firmware itself. So yeah, my time is running out, but just like to give you some key takeaways. MCCS is a pretty rich attack surface for the monitor. I think it's been kind of neglected over time because display monitors are not the most exciting attack surface. But I think over time, we've seen a lot more introduction of features to display monitors and what you can do with them. There are also multiple host to monitor and monitor to host exploit scenarios. So it's not just about exploiting the display monitor itself, but in this case, by manipulating the responses from the display monitor, you can actually get an exploit on the host that's connecting to it. And generally speaking, what I've seen is that MCCS response data is unsafely trusted by the majority of manufacturer-supported software out there. It's kind of weird, but I guess no one expects to be pwned by the display monitor. And default display monitor software in general has been weak, so I've surveyed dozens of them by now, and most of them don't really handle basic memory stuff that you would typically expect in more hardware connected software these days. So actually, it is pretty interesting, but you just need to find the right manufacturers as well as the handling of the untrusted sources. Cool. I think got some time for questions now.
Yep, we got time for questions.
So while I agree that MCCS as an attack surface is intellectually interesting on the monitor itself, do you have any evidence that any of these monitors are implementing anything like secure boot that would prevent you from just getting arbitrary code execution on them by a corrupted like firmware update? Like, can you just send a modified firmware and you get arbitrary code that way?
It's definitely doable. So as mentioned, Max Thomas has kind of done a live flashing of the what's running on the monitor itself, firmware itself. There's not a lot of protections, maybe some encryption of the firmware when you do flash it, but overall it's kind of hard to figure out as well because, as mentioned, it's very specific chipsets, like the Genesis chipset, and very specific instruction sets that are not great, that don't work well in your typical reverse engineering software. So I've looked at it, but haven't made much progress there.
Okay, I was more interested in whether you on different monitors than have been looked at thus far. And then on your example of host to monitor exploitation, I believe you were looking at like a read serial number opcode type thing. You said there was like a sanity check in there of like check for 5 or something like that, but I wasn't clear since you went through it quickly. Were you saying that that particular opcode could still read like arbitrary memory and therefore it could be used to like dump the entire memory? And if so, then my question is there a separation of the memory between display data type stuff versus the code? So like, could you dump the firmware in that way instead of having to do as much reverse engineering?
Yeah. So you can read beyond the offset in the Acer monitor itself, but I haven't been able to see any, like, it's mostly just null, so like ones. So I doubt that is actually display monitor, what's actually being displayed on there. But what we've seen from other research is that it kind of exists somewhere in the display monitor software, but I'm not sure if it's actually separated per se. Yeah.
Okay. And then for that one specifically, I think later on you said that that could potentially be used for read or write, or like in your conclusions for the host monitor exploitation, you said something about read or write, but I wasn't clear. Was there an example specifically of write that you would like confirmed?
Yeah. So I haven't found a write gadget over MCCS, but as mentioned, other researchers have found write gadgets through other protocols, such as gprobe or other protocols. So yeah, I'd love to find one in MCCS specifically. But sure. MCCS right now, what I've seen is just this read gadget.
All right, thank you.
Any other questions?
Thanks, great talk. So I see your research is mostly focused on physical access for both monitor and the host itself. Have you thought about wireless scenarios too? Like, and does it any of those research correspond to those like Miracast and all those?
Yeah, so that's an interesting part of research. Most of the monitors I work with is just consumer grade, like monitors that don't have network capabilities. But what I've seen with some of the display monitor firmware, for example, let's see. With the NEC stuff, they do work with more commercial grade monitors and displays, LEDs, that do work over the network. So that would be kind of something I'll be interested to look at as well. But so far, what I've seen primarily at the consumer grade level is that you see local network stuff. So features like HP's device transfer, bridge transfer that allows you to copy files between monitors. But that actually works through their own software that's, again, running on your host. So it doesn't actually go through the monitor itself.
Got it. Yeah, thank you.
Any other questions? All right, well, let's give Eugene a final round of applause. Thank you. One more question? Awesome. Sorry I missed you.
Sorry about that.
Yeah, great presentation. I was just curious because I had some sort of experience with Windows Debugger, and I was just curious because I noticed you didn't talk about, did you find any sort of symbols or data structures that when you were trying to do an analysis, did you explore those and see where you can find out? Just something to put into consideration.
Symbols meaning when reverse engineering the software?
Yeah.
Not specifically. So for the .NET assemblies, it's basically almost like a one-to-one. But most of the time, they do call backing DLLs that use the low-level APIs, but not a lot of symbols. The data structures are fairly simple for MCCS. It's usually just 1 byte for the value and 1 byte for the opcode. So not particularly. Yeah.
Thank you.
All right. Now there's no more questions.
Cool. Thank you.
Thank you.